You ever hear that an AI is 99% accurate and think, wow, that's basically perfect? Of course you have. We all do. But what if I told you that number, that really impressive number, can actually be a huge lie? We're going to pull back the curtain and see exactly why that percentage might be hiding a total catastrophic failure.
And this, right here, just gets straight to the point. You can have a model that looks fantastic on a spreadsheet, but is completely useless in the real world. A fraud detector that's 95% accurate but catches zero fraud? That's not just a bad model, it's dangerous. It gives you a false sense of security. I mean, really, what good is a security system that never, ever catches the thief?
I know, it sounds dramatic, but it's true. A single accuracy score can paint this beautiful picture of success while the model is failing in the one job it was designed to do. So let's dive in and see exactly how this deception works and, more importantly, how you can spot it a mile away.
Okay, so where does this lie even come from? Well, a lot of the time, the problem isn't the AI model itself, but the data we feed it. It all comes down to this really important concept called class imbalance. And trust me, it's the #1 reason why accuracy can be so misleading.
So what is class imbalance? It's when the thing you're actually looking for is super rare. Think about it. In a huge batch of financial transactions, the fraudulent ones are a tiny fraction. Or for medical screening, most people, thankfully, are healthy. So when one class, like healthy, makes up 99% of your data, a lazy AI can just learn a simple trick to look smart.
And this cancer screening example just blows the whole myth wide open. Okay, look at this. You have 1,000 patients. Only 10 have cancer. Now, a lazy AI model could just predict healthy for every single person. And guess what? It gets 990 of them right. That gives it a 99% accuracy score. But it found 0 cancer cases. It is 99% accurate and 100% useless. See the problem?
So, to see past that one misleading number, we need a better tool. We need something that breaks down how the model is actually doing, where it's getting things right, and more importantly, where it's getting things wrong. That tool is called the confusion matrix.
You know, for any prediction, especially a simple yes or no kind of thing, there are really only 4 things that can happen. The model can be right in 2 different ways, and it can be wrong in 2 different ways. Understanding these 4 outcomes, that's the key to getting the real story.
And this is it, the confusion matrix. Think of it like a detective's evidence board. On one side, you have the actual truth, what really happened. On the other side, you have what the AI predicted. By sorting every single prediction into one of these 4 boxes, we start to see what's really going on.
First up, the true positive. This is the easy one, a clear win. The model was supposed to find cancer, and it found cancer. Perfect, it got it right.
Next, the true negative. This is the other kind of win. The model correctly gave the all clear. It said healthy, and the person was, in fact, healthy. This is the quiet hero that makes up most of the correct predictions in these imbalanced datasets.
All right, now for the mistakes. A false positive is basically a false alarm. The model cried wolf. It said cancer, but the person was healthy. Now, this can cause a lot of stress and maybe some unnecessary tests, but at least the mistake was on the side of caution.
But this is the one we really have to worry about. A false negative is a missed case. The model gave the all clear when it absolutely shouldn't have. It said healthy, but the patient actually had cancer. This is the kind of error that can be, quite literally, fatal.
So once you understand these 4 outcomes, you realize that building a good model isn't about one goal. It's about a constant tug of war, a trade-off between 2 competing goals, precision and recall. And the tricky part is, when you try to improve one, you often make the other one worse.
The easiest way to wrap your head around this is to think of them as asking 2 totally different questions. Precision asks, of all the times we flagged something as positive, how often were we actually right? This is all about not having false alarms. On the other hand, recall asks, of all the positive cases that were really out there, how many did we manage to find? This is about not missing anything.
So precision is all about quality over quantity. When precision is high, it means that when the model says, hey, I found something, you can be pretty darn sure it's the real deal. Fewer false alarms.
A perfect example? Your email's spam filter. You absolutely need high precision here. Why? Because a false positive, a super important email getting lost in your spam folder, is a way bigger problem than a couple of junk emails getting into your inbox. Now, recall is the opposite. It's all about quantity and coverage. It's casting a wide net to catch as many fish as possible. High recall means the model is fantastic at finding everything it's supposed to find.
leaving no stone unturned. And let's go back to our cancer screening example. Here, the game totally flips. You need high recall. A false negative, telling a sick person they're healthy, is the absolute worst-case scenario. You would much rather have a few false alarms that lead to more tests than miss even a single actual case.
So we have this constant battle between precision and recall. How on earth do you find the right balance? Is there a single number that can give us a more honest look at the model? Well, yes there is, and it's called the F1 score.
And this is why the F1 score is so great. It's the ultimate lie detector. Remember that 99% accurate model that found 0 cancer? Its F1 score would be a big fat 0. The F1 score calls out that lazy model for what it is: useless.
So what is it? It's the harmonic mean of precision and recall. Now that sounds fancy, but the key idea is simple. Unlike a regular average, the harmonic mean gets punished hard if either number is low. It's like a chain. It's only as strong as its weakest link. To get a high F1 score, you have to be good at both precision and recall. There's no cheating.
So, we've torn down accuracy, we've explored the confusion matrix, and we've understood the battle between precision and recall. Let's bring it all home. With this new toolkit, you can finally move beyond that one simple, misleading number and start asking the questions that really matter.
So, which metric should you trust? Well, the most important thing to remember is there's no single best metric. It always depends on the problem you're trying to solve. If your data is perfectly balanced, sure, accuracy can be fine. But for almost everything else, you have to ask, what's the cost of being wrong? Is a false alarm worse, or is a missed case worse? Answering that question tells you whether to focus on precision, recall, or the F1 score for a balanced view.
So I'll leave you with this thought. The next time you see a headline or someone in a meeting says an AI is highly accurate, you'll know that's not the end of the story. It's just the beginning. You'll know to dig a little deeper and ask the right questions. Okay, but what's the precision? And what's the recall? And for this specific problem, which of those two really truly matters more?